Hi, and welcome back to SWECODES. In this series of the basic foundations of programming, we will be diving deep into the fundamental building blocks of programs and programming languages. These are core concepts you must know before starting your journey into becoming a proficient software engineer. There will be more chapters coming up after this. So let's get started. Chapter 1: Programming Principles. Every single app, website, and smart device you use is a long list of instructions, invisible steps that tell your computer exactly what to do, line by line. This is programming. A program is simply a precise recipe for computation, a set of instructions a computer follows to complete a task. Whether it is solving complex equations, calculating a budget, or even recognizing your voice, under the hood, it is math, logic, and structure organized in code. Here is the simplest example possible: the Hello World program in C. It tells your computer to print two words on the screen: Hello World. That is one instruction, one outcome. The building blocks of computation. Every program, no matter how advanced, is built from the same basic actions. 1. Getting data, reading input from a keyboard, file, or device. 2. Processing data, performing calculations or logical decisions. 3. Making choices, checking conditions like, if this happens, do that. 4. Outputting results, displaying something on screen or saving it somewhere. These 4 ideas form the backbone of all programming. Everything else is built on top of them. Programming isn't just about typing code. It's about thinking systematically. You take a big, messy real-world goal and divide it into smaller and smaller tasks until each one is simple enough for a computer to execute directly. Think of it like this. The big task: translate a book. Break it down, translate each chapter. Then each paragraph. Then each word. Eventually, every small step is so clear the computer can follow it without confusion. That's the essence of computational thinking, and it's why great programmers are great problem solvers. Once you understand this, everything in computer science clicks into place. Machine learning models? Just programs that adjust their own instructions. Web apps? Programs that listen and respond to your input in real time. Even your phone's alarm clock? Still just a program following a sequence of timed instructions. When you learn to program, you're not just learning syntax. You're learning how to think like a computer and design solutions that scale. So the next time you see a line of code, remember, it's not about symbols or jargon. It's about logic turned into action. If you can think clearly enough to break down any problem into steps, you already think like a programmer. And that's the foundation of every great innovation in tech. Every app you use, every website you visit, every line of code, it's all part of a conversation. But how do we as humans talk to a machine? You can't just tell your computer, run my payroll. It requires a translator. It requires a programming language. It's helpful to think of 2 levels of these languages. At the very bottom, there's low-level language. This is the native tongue of your processor. It's not really one language. It's a set of precise instructions specific to the hardware, like the architecture in your phone. An ARM chip, or your laptop. An Intel chip. This is as close to the metal as you can get. The advantage? Speed and control. A low-level program can be perfectly tuned for a specific computer, giving you maximum execution speed while using the absolute minimum memory. The trade-off? It's incredibly difficult, time-consuming, and cryptic for humans to write, read, or correct. This is why, for almost everything else, we use high-level languages. These are the languages you've heard of: Python, Java, Perl, C++. They are a layer of abstraction. They are designed for humans. They read more like plain English, allowing you to tell the computer what to do without worrying about the millions of tiny steps the hardware needs to take. The advantages here are all about human efficiency. They are far easier to program, meaning less development time. They are easier for people to read and, crucially, easy underscore. R underscore. To correct or debug. And the killer feature, portability. You can write code once and, with minimal changes, run it on a completely different computer. But this creates a paradox. If computers only speak low-level languages, how do they run high-level code? They use that translator. A special program called a compiler or an interpreter does the heavy lifting. It meticulously translates your human-readable, high-level instructions into the thousands of specific, low-level machine commands the computer actually understands. Today, almost all programs are written in high-level languages. We've made a fundamental choice. We trade a tiny, often unnoticeable fraction of machine speed for a massive gain in human productivity. And that is what allows us to build the complex, powerful, and amazing digital world we rely on every single day. This simple block of code is your key to C programming. It just prints "Hello World." But to a professional, it's not one program. It's 5 distinct components. Forget "Hello World." The goal here is to have the mental model to read any C program. Let's deconstruct it. First, line 1, /* hello world program */. This is a comment. The compiler, the tool that builds your program, completely ignores everything between the /* and */. This isn't code, it's a note for humans. Why? Because the person who has to maintain your code 6 months from now might be you. In a professional environment, this is non-negotiable. It's how you explain the why behind your code, refresh your memory, and allow others to collaborate. Uncommented code is technical debt. Line 2, # includes stio.h. This is a preprocessor directive. It's an instruction that runs before your code compiles. It tells the compiler, go find the file named stio.h and include its contents right here. This is the core concept of code reuse. We don't want to write the low-level logic for printing to a screen every time. Stio.h stands for the Standard Input-Output Library. It's a pre-built toolbox, and we're importing it to use one of its tools. Line 4, int main. This is the single most important line. Every C program in existence must have a main function. It is the non-negotiable entry point of your application. When you run your program, the operating system looks directly for main and begins executing whatever it finds inside these curly braces. This is the engine of your code. Without it, nothing happens. Everything inside those braces is the body of the function. This is where you write your instructions. Here, we only have 2. Let's analyze this line, printf, hello world. It's actually 2 distinct parts. Printf is the command, or more accurately, the function. This is the tool we imported from stio.h. And hello world is the data, in this case a text string, that we are passing to that function. You're simply saying, execute the print formatted command and use this text as its input. Finally, the most critical piece of syntax, the semicolon. In C, the semicolon is not optional. It is the instruction terminator. It tells the compiler, this command is finished. Stop here and prepare for the next instruction. Forgetting this is the single most common error for new C programmers. You now have the 5-part model to read any C program. You write code. You hit run. Magic happens. But what is that magic? The code you write, your source code, is just text. Your processor, the CPU, can't understand a single word of it. Your CPU only speaks one language, raw machine code. To bridge this gap, your code must be translated. But how it's translated is one of the most fundamental concepts in programming. This isn't just theory. It defines your debugging workflow, your program speed, and even the language you choose. There are 2 main ways to do this: interpreting and compiling. First, let's meet the interpreter. Think of an interpreter as a live, simultaneous translator at a UN meeting. They listen to one sentence, translate it, and say it. Then they listen to the next. This is exactly how an interpreter works with your code. Step 1. It reads your first line of code. Step 2. It translates just that one line into machine instructions. Step 3. The CPU executes those instructions immediately. Step 4. It moves to line 2 and repeats the process. This line-by-line model is standard for languages like Python, Ruby, and PHP. The upside? It's fast to start and easy to test. The big gotcha? If you have a critical bug on line 50, your program will run perfectly through lines 1 to 49 every single time before it finally fails. This can waste a lot of time during execution. Now meet the compiler. A compiler isn't a live translator. It's a master scholar who translates your entire book from English to Latin before anyone is allowed to read it. This is a multi-step process. Step 1. Compiling. The compiler scans your entire program, every file, every line, all at once. It checks for syntax errors, type mismatches, and other issues before a single line is ever run. It finds that bug on line 50 instantly. Step 2. Object code. If everything checks out, The compiler translates your source code into a file called object code. This is almost machine code, but it's not quite ready. Step 3. Linking. Your program needs help. It has to connect to other pre-written library code, like the code needed to print text to the screen. A separate program called a linker connects your object code to those libraries. Step 4. The executable. The linker bundles everything into a single, standalone executable file. This is the standard for languages like C, C++, and Go. When you run this file, it's 100% pure, optimized machine code. The translation work is already done, making it incredibly fast. So, what's the real-world difference? An interpreter translates line by line at runtime. This is flexible and great for development, but it's slower to run and finds errors late. A compiler translates everything before runtime. This catches errors early and produces a highly optimized executable file that runs extremely fast. But here's the pro-level secret. It's not always one or the other. Many modern languages, like Java and C#, use a hybrid model. They compile the source code into an intermediate language called bytecode. Then, a virtual machine acts as an interpreter to run that bytecode. This gives you the best of both worlds: the error checking of a compiler and the platform independence of an interpreter. Understanding this execution model is key to mastering programming. It's the difference between a program that's built for raw speed and one that's built for flexibility. Now you know what's really happening when you click Run. A variable is not just a box for a value. That's incomplete, and in C it's misleading. A variable is a name, a label you create that refers to a specific location in memory. This distinction is critical for understanding C. Before you can use that name, you must tell the compiler what kind of data it will point to. This is its type. We'll start with the most common type, int, which stands for integer or a whole number. When you write int score, you aren't just creating a name. You are giving the C compiler a specific command. Find an empty spot in memory and allocate just enough space to hold one integer. The type tells the compiler the size of the memory to reserve. This concept of precise memory management is fundamental to C's power and performance. The variable score becomes your human-readable name for that specific, allocated memory address. So, how do we create these names? C is flexible, but it has firm rules. Get this right, and your code is clean. Get it wrong, and it won't even compile. Here's what you can use: uppercase letters A through Z, lowercase letters A through Z, digits 0 through 9, and the underscore character, underscore symbol. Those are your only building blocks. So names like A_mient or _mient99 are all perfectly valid. Now the common pitfalls. The compiler is very literal, so these rules are not suggestions. First, a variable name cannot start with a digit. 221b is invalid. The compiler reads the 2 and expects a number, not a name. Second, no spaces. My score looks like two separate commands to the compiler. If you need a space, use an underscore like my_score or use camel case like myscore. Third, no other symbols. Forget $signs, percentages, or question marks. $1 is invalid. Finally, there's a short list of words that C reserves for its own syntax. These are called keywords or reserved words. You cannot name a variable int or float or while. These words are the very tools C uses to understand your logic. Trying to use them as a name will confuse the compiler completely. You can easily find a full list of these keywords online. Master these 4 steps: understanding memory, defining types, and following the naming rules, and you've mastered the single most essential building block of C programming. Every single useful program, from a simple mobile app to a complex operating system, runs on one core concept: storing information. Get this concept wrong, and your entire program fails before it even starts. We're talking about variables. Think of a variable as a labeled empty box, ready to hold one specific type of thing. Building this box is the first critical step: declaration. When you declare a variable, you're not giving it a value. You are simply reserving a space in the computer's memory. You have to tell the system 2 things. Asterisk, what type of data will it hold? A whole number? Text. A true/false value? What is its unique name? We've just reserved a box for a whole number, and we've put the label mean on it. That's declaration. The box is reserved, but it's still empty. An empty box isn't useful. The second step is assignment. This is when we put something inside the box. We use an assignment operator, usually an equals sign, to do this. When we say my int equals 7, we are telling the program, find the box labeled my int and put the value 7 inside it. This very first time you assign a value to a variable is a critical technical term, instantiation. You are giving the variable its first instance of a value. You've taken it from an abstract idea to a concrete thing. So, to recap, declaration creates the box. Assignment fills the box. Now, let's be efficient. This two-step process, declaring then assigning, is valid, but in modern programming, you'll almost always combine them. This is the third concept, initialization. Initialization is the act of declaring and assigning a value in one single statement. Instead of reserving an empty box and filling it later, we say, create a new box for a whole number, label it other var, and immediately put the number 4 inside. This is cleaner, faster, and the standard way to create variables. You've declared its type and instantiated its value all at once. This brings us to the final, most important concept, the one that gives variables their name. Their value can vary. Once a variable is declared, you can change its value anytime. This is called reassignment. Our myInt box is holding the number 7. We can now say myInt equals 4. The computer finds the existing box, throws out the old value 7, and replaces it with 4. The old value is gone forever. But here is the critical rule. You only declare it once. You can reassign a new value 1,000 times, but you must never try to declare a variable with the same name again in the same scope. The box is already built. You don't build a new box with the same label. You just change the contents of the one you have. These 4 actions, declaration, assignment, initialization, and reassignment, are the most fundamental building block of all programming. You write your first program. You hit run. And it fails. You get a cryptic error, undeclared identifier, name not found, or just a total crash. What went wrong? This is the single most common stumbling block in programming. It's not a complex bug, it's an order error. And fixing it teaches you the fundamental logic of how a computer actually thinks. Let's look at this broken program. Inside our main function, the program's front door, we have 2 instructions. Instruction 1, printf. The integer is %d\NA. In plain English, this line commands the computer. Print a message to the screen, and where you see that %d, a placeholder for an integer, I want you to insert the value of a variable named a. Instruction 2, int a equals 7. This line commands the computer. Create a new box in memory, label it a, make sure it can only hold an integer, and put the number 7 inside it. This is called variable declaration, creating the box, and initialization, putting 7 in it. Here's the problem. Computers are incredibly fast, but they are not psychic. They execute your code sequentially, one line at a time, from top to bottom. At line 1, you asked it to use the value in box A. But at that exact moment, the computer has no idea what it is. You haven't built the box yet. It stops and throws an error, effectively saying, "What is A?" You never defined it. So, how do we fix it? We simply reverse the order. We obey the rule of declaration before use. New instruction 1, int a equals 7. First, we tell the computer, create the integer variable a and store the value 7 in it. The computer now knows it exists and what its value is. New instruction 2, printf. The integer is %d\N, a. Now, when the computer reaches this line, it's easy. It knows exactly what it is. It goes to that memory location, fetches the value 7, and prints it to the screen. And it works perfectly. This isn't just a C language rule. This is a fundamental principle of programming logic. Think of it like a recipe. You can't stir the eggs, the action, before you crack the eggs, the declaration. Think of your program as a dictionary. You can't look up a word, like a, that hasn't been written in the dictionary yet. The declaration is the act of writing the word and its definition. The access is looking it up. This concept is the root of variable scope, compilation, and linkage, all critical, high-level topics in software engineering. But they all start with this one non-negotiable rule. Define it before you use it. The next time you get an undeclared error, don't panic. Your first check is always, did I spell it right? And your second is, did I declare it before I tried to use it? Master this, and you've just mastered step 1 of thinking like a programmer. You've printed Hello World. Congratulations. But now the real work begins. How do you print the value of a variable? This is the first critical hurdle where many new C programmers get stuck. You have a variable, int a equals 7. How do you get that 7 onto the screen? If you simply write printf, a, you get the letter A, not its value. The key to unlocking your program's data and displaying it is a mechanism called format specifiers. Let's analyze this line. This is a more complex printf call. Notice it takes two arguments, separated by a comma. This is the entire secret. The first argument is your template, known as the format string. It's the literal text you want to print, but it contains a special command. That command is %d. This is your format specifier. The %% is a signal to the printf function. It says, stop printing text literally. Treat what comes next as a placeholder. The d specifically stands for decimal integer. Think of %d as a contract. It's a promise to printf that, at this exact spot in the string, you will provide an integer variable, and it should print that variable's value here. The second argument, a, is the data that fulfills that contract. When printf sees %d, it pauses, looks for the next argument, finds a, retrieves its value, which is 7, and inserts it. The result, the static text the integer is printed. The %d is swapped at runtime for the value 7 and the \n. New line character moves the cursor to the next line. You have successfully created dynamic output. This pattern is essential because it scales. What if you have two variables? You simply use two format specifiers. Printf processes them in a strict first-come, first-served queue. The first %d maps to the first variable, a. The second %d maps to the second variable, b. The order is critical. The output is exactly what you'd expect. A is 7 and b is 50. You must provide one matching variable for every format specifier you use. You now understand the fundamental bridge between your program's memory and the user's screen. This %d for integers is just the start. The same principle applies to printing text, floating point numbers, and more. You've been using int. It works. But just using int in C is like a chef only using one knife. Your code runs, but it's not efficient. It's not precise. And it could be wasting memory. In C, data type selection is optimization. You're not just storing data. You're reserving a specific box in memory. The type defines the size and shape of that box. We've moved past just int. Let's break down the 4 essential types. First, int. This is your workhorse for whole numbers. Think counts, loops, or IDs. On most systems, it reserves 4 bytes, or 32 bits, of memory. Second, char. This is for single characters. But here's the pro tip. A char is just a tiny integer. It's a single byte, 8 bits. So, the letter A is stored as the number 65. This is the bedrock of all text in C. Now for decimal numbers. C gives you two options, float and double. Why 2? It's a critical precision versus memory trade-off. A float uses 32 bits. It's fast, but it's only accurate to about 7 decimal places. A double, which just means double precision, uses twice the memory, 64 bits. Your reward? Pinpoint accuracy to 15 or 16 decimal places. The takeaway? Using a float for financial calculations? You'll create rounding errors. Using a double for simple graphics? You're wasting memory. Choose the right tool. This is where you graduate from beginner to professional. You don't just use the types, you modify them. Let's look at signed versus unsigned. By default, an int is signed. That means it splits its 4 bytes of data to represent negative and positive numbers. Roughly -2 billion to +2 billion. But what if you're storing something that can't be negative? Like an age or a user ID. You declare it as unsigned. You're telling C, don't waste half this box on negative values I'll never use. You just doubled your maximum positive value. You've reclaimed that negative bit and added it to the positive side. That is smart memory management. And there's one more layer, short and long. These modifiers directly control the size of the box. Need a small number and want to save memory on thousands of variables? Use a short int. Need to store a number larger than 2 billion? You must use a long int, or even a long. Applying long to a double gives you even more precision. Mastering C data types isn't academic. It's the difference between bloated, buggy code and a fast, efficient, reliable program. You're not just storing a number. You are defining its range, its precision, and its memory footprint. That is programming. Every programmer on Earth, from beginner to senior architect, hits this wall. They're called bugs. But not all bugs are created equal. Knowing what kind of error you're facing is the secret to fixing it fast. This isn't just about fixing code. It's about building a framework for problem solving. We're dissecting the 3 types of errors every programmer must know. Master this, and you'll debug 10x faster. First up, the syntax error. Think of this as a grammar or spelling mistake for the computer. Programming languages like C have strict rules, the syntax. If you break those rules, the compiler, which translates your code into machine language, will stop and complain. Look at this Hello World program. Can you spot the bug? It's right here. In C, every statement must end with a semicolon. It's like the period at the end of a sentence. We missed it. The good news? Syntax errors are the easiest to fix. The compiler literally won't build your program and will usually tell you the exact line number where it got confused. It's your first line of defense. The second type is more dangerous. The runtime error, also known as an exception. This bug is sneaky. Your code is grammatically perfect. It has no syntax errors. It compiles. It starts to run. But then, halfway through, the program crashes. Why? Because you gave it an impossible command that it only discovered while running. Look at this code. We create a variable a and set it to 0. Then we try to print the result of 5 divided by a. This is a fatal problem. In mathematics, you cannot divide by 0. The compiler didn't know it would be 0, but when the program ran and got to this line, boom. It's an exceptional event, and the program terminates. Runtime errors are harder to find because they can depend on user input or hardware. This is why robustness, writing code that anticipates these problems, is a critical skill. This last one is the most difficult and the most dangerous, the logical error. The code has no syntax errors. It compiles. The code has no runtime errors. It runs to completion. And it gives you the wrong answer. Why? Because the program did exactly what you told it to do. The problem is, what you told it to do was wrong. The intent of this code was to find half of the variable n. Half of 4.0 should be 2.0. But the program outputs 0.5. The mistake is right here. The programmer meant to write n/2.0, which is n divided by 2. But they actually wrote 2.0/n, which is 2 divided by n. The computer just followed the faulty instructions perfectly. This is the silent killer of bugs. And here's the scariest part. What if the variable n just happened to be 2.0? The result would be 1.0. The math n/2.0, 2/2, and 2.0/n, 2/2, both equal 1. The bug would be completely hidden. You wouldn't know the error existed until n changed to a different value. This is why debugging is one of the key skills in programming. It's not about avoiding bugs, you can't. It's about learning to find them, and finding them starts with knowing what you're looking for. So, to review. Syntax errors, grammar mistakes the compiler catches. Runtime errors, impossible commands that crash the program. Logical errors, flawed thinking that produces the wrong result. Your job as a developer isn't to never write bugs. It's to be a world-class debugger. Now that you can identify what bug you have, the next step is learning how to find it. In our next lesson, we'll dive into the essential tools and techniques for practical debugging. You've been told debugging is a chore, a tedious cleanup after the real programming is done. That's wrong. Debugging is the most intellectually challenging, creative, and critical skill in all of software development. It's not janitorial work, it's detective work. When you see a bug, you're not seeing a mistake. You're seeing a clue. Your program is giving you a perfectly logical result based on the instructions you gave it. The output is the scene of the crime. Your job, like Sherlock Holmes's, is to use these clues to infer the hidden events that led to the result. You must ask, what must be true inside the machine for this specific, weird behavior to happen? When you've eliminated the impossible, whatever remains, however improbable, must be the truth. This detective work isn't just intuition, it's the scientific method. This is the core process of all debugging. 1. Form a hypothesis. Based on the clues, you guess. I believe the error is in the API authentication logic. 2. Design an experiment. You don't just randomly change things. You design a specific test. I will send a request without a valid token and observe the response. 3. Observe the results. You run the test. What happened? Did it fail the way you expected? Or did something new and unexpected occur? 4. Refine your hypothesis. The result, the new clue, narrows the search. You repeat the loop, getting closer to the truth with every cycle. Here is the most important takeaway. At a professional level, programming and debugging converge. They become the same activity. You are never just writing new code. You are debugging a program until it does what you want. Think about it. You start with an empty file, a program that does nothing. That's your first bug. You add a line of code. You run it. You've made one small modification, and you immediately test or debug it to see if it does what you intended. This is the entire foundation of modern techniques like test-driven development, TDD, and agile programming. The most effective programmers build on this principle. Their secret? They always have a working program. They start with the simplest possible thing that works. They make one small modification. They test it. They debug it. Once it's working again, they make the next small modification. This incremental loop is how you build massive, complex systems without getting lost. Need proof? The Linux operating system started this way. Linus Torvalds didn't try to build a giant OS. His very first program was just an experiment to test the Intel 80386 chip. It did nothing but switch between printing quad A and BBBB on the screen. That's it. A tiny working program. He made a small modification. He debugged it. He made another. And another. 25 years of tiny modifications and debugging loops later, that quad A/BBBB program evolved into the kernel that runs our modern world. So, change your mindset. You're not a writer or a fixer. You are an investigator. And every bug is just a clue pulling you toward a better solution. Stay tuned, as in our next video, we will be discussing functions and parameters in the basic foundations of programming.